Good morning. I'm very happy to welcome you to this morning's plenary lecture by Maciej Zworski. Maciej received his PhD in mathematics from MIT. We didn't agree ahead of time that I could say the year, so I will not, where he worked with Richard Melrose. After that, he went on to Harvard for a Benjamin Pierce lectureship, and then was associate professor and professor at Johns Hopkins, afterwards professor at Toronto, and finally he's a professor at UC Berkeley. So he's received a number of awards and accolades for his work, with just a few examples, including the Sierpinski Medal of the Polish Mathematical Society, an honorary doctorate from Paris-Sous, and a Simons Fellowship in Math. He's a fellow of both the American Academy of Arts and Sciences and the Royal Society of Canada. And he's also given a number of distinguished lectures and lecture series around the world. So Professor Zworski is a leading expert in semi-classical or microlocal analysis, and he's motivated by questions in mathematical physics, especially mathematical aspects of classical quantum correspondence and its manifestations in PDE. His work, especially that on scattering resonances, has had a huge impact on the field. And the impact of his research has been amplified by his incredible track record as a mentor to early career researchers, helping them to launch successful careers at places such as MIT, Brown, Purdue, UNC, the University of Washington, and University College London. This mentoring work was recognized by a faculty mentor award of the Graduate Assembly from Berkeley. And Professor Zworski has also been active in nonprofit scientific publishing, serving as founding editor-in-chief of Pure and Applied Analysis and a longtime editor for Analysis in PDE. So finally, Professor Zworski is a noted expositor and speaker and has a wicked, self-effacing sense of humor. And I'm sure that he has a wonderful and entertaining lecture in store for us. Please welcome Maciej Zworski, who will speak on postmodern semi-classical analysis.
Okay, so it will be a little hard to live up to the expectations set by Professor Stovall here, but I will try. So I have a somewhat bombastic title. So, I have to first tell you what the terms in the title mean. So, what is postmodernism? So this is a famous example from Miami. Postmodernism is, you know it when you see it. But I actually took the definition from a paper of 30 years ago by physicist Helen Tomsovich, who wrote an interesting paper called Postmodern Quantum Mechanics. And I just let you read the introduction explaining what postmodernism is in arts. The idea is that you revisit the origins of the subject or a movement from the perspective of what one has gained through its, not study, but development. In quantum mechanics, this is what they wrote, that basically one could return to the origins of quantum mechanics and investigate them in view of modern developments. And one can paraphrase it in the context of microlocal analysis, which I will also explain. And we can revisit the origins of the subject or even reinterpret the origins of the subject from the perspective of both progress in mathematics, but also computational power that certainly did not exist at the time when the subject started, and also new questions in science. So what is microlocal analysis? So a postmodern definition is that it is a use of classical quantum correspondence in partial differential equations and other fields of mathematics. So what is classical in quantum correspondence? So I'll first illustrate it by a movie. So, classical mechanics is described by Newton's equation from 1687, and quantum mechanics by Schrödinger equation from 100 years ago, exactly 100 years ago. And, if I plot here a solution of the Schrödinger equation, solution of the Newton's equation, one sees that there is some analogy between the behavior of the solution of the Schrödinger equation, or the wave function, and this classical particle. Of course, something happens, and the agreement is not perfect, and it's actually affected by the classical mechanics. The actual origins of the subject in mathematics were different, at least sort of if you look at the history of it. And it came from singular integral operators, several complex variables. In fact, that was the motivation of famous paper of Kohn and Nirenberg, which introduced you to differential operators, index theory, and regularity of solutions to PD, spectral geometry. So I cannot, in this talk, do justice to this development or describe the contributions of many famous mathematicians. The term itself was coined by Sato in a talk in Orsay in 1973, and I don't know what Sato meant really, but I thought that one way to explain it is that you consider functions simultaneously in position and frequency. Of course, within the rules imposed by the uncertainty principle. And hence, if you do it simultaneously, locally, in position and frequency, you somehow look at your functions or distributions microlocally. And I add a personal note, and as Betsy mentioned, I learned this subject from Richard Melrose in the context of mixed boundary value problems. And actually, Melrose-Taylor parametrics, which is sort of halfway between now and Schrödinger equation. It's kind of a scary thought for me, that is to say, is still useful today. So to say, what do I mean by classical? Well, again, we have Newton's equations, so we have a conserved quantity, the energy. So here, without any physical constants and so on, we have position x, momentum psi, and the kinetic energy is psi squared, potential energy is v of x. So there's high school physics, and Newton's equations say that a particle in this potential field will evolve according to these equations. So that the velocity is essentially the momentum, and the momentum. There's prime missing. Is given, the psi prime is v prime, which is the force in this potential field. And, in the 19th century, this was vastly developed, and we would now call it a symplectic point of view, namely that we think about this evolution as the flow of the Hamilton vector field of this Hamiltonian P of x and psi. And I will just stick to the Euclidean case in this talk. So the Hamilton vector field is given by this formula here. And as you can see, it preserves P, because if I apply it to P, I get 0, unless, of course, I made some mistake, which I did. I've been in this business for so long. The derivative with respect to, the second derivative is with respect to x. Yes, that's partial psi p dx, partial psi xp d psi. And you see that this corresponds to Newton's equation, and it preserves p. So on the quantum level, the evolution is governed by the Schrödinger equation. And the Schrödinger equation is obtained by quantizing this classical Hamiltonian. And the quantization procedure that we learn in first courses in quantum mechanics is that we turn classical observables, functions of position momentum, into operators. And we do this by replacing the momentum by h times capital dx, and capital dx is 1 over I partial x, so that it's formally self-adjoint. So this is a PD notation. And h here does not really mean Planck constant, it means a small number, because there are many other constants, mass, whatever, and it may mean all sorts of things here. And the quantum state is described by a wave function which evolves according to the Schrödinger equation. And, this was written 100 years ago. But one of the problems with any PD, even sort of relatively simple PD like that, is that you cannot solve it, in an explicit way. So shortly afterwards, actually, and shortly before, a method of approximate solutions, which actually is extremely accurate, was developed in famous work, independent work of Wenzel Kramer-Brouillon in 1926. And that's an approximation of solutions as h goes to 0. In fact, Jeffreys produced finer work and more general work 3 years before, but it's kind of rarely remembered. It's always WKB. So I looked up Jeffreys' paper, and he also uses h, but his h actually goes to infinity. It's 1 over h of this problem. So, he was ahead of the quantum revolution, so to speak. And what is this WKB approximation? So the simplest form is taking the following approximation of the solution of the Schrödinger equation. Namely, you have some slowly varying amplitude and then a highly oscillatory term as h goes to 0. So, it's not difficult, especially in one dimension, to look at what equations are satisfied by A and phi. You just plug it in and you get it. So what you get is this equation. You turn a highly oscillatory problem to a simple nonlinear problem. But this type of equations, first-order scalar equations, can be solved. And here is the solution of this given implicitly. And as you can see, the solution to the equation for phi is given in terms of the classical evolution. So the WKB approximation links the classical picture with the quantum picture. So a few more words about it. You can also consider it without time. It's a little simpler. Again, in 1D, let's say. In that case, you have the following approximation, where phi again solves phi solves the equation similar to the one we had before. And again, this equation can be solved. And what I would like to point out is that if I apply h dx minus phi x to my approximation, what you get is an error of size h. Since psi corresponds to h dx in this quantization, this means that this WKB state is localized in momentum to psi equals to phi of x. And since this localization is on scale of O of h, I can't maybe go to many details, by the uncertainty principle, it has to be delocalized in space. And it is, because you just have this amplitude. In this case, it's v of x to the power minus 1/4. Well, this breaks down when v is 0, but there are ways to, and that was actually done by the WKB crowd 100 years ago. You can match it through places where v is equal to 0. And this is actually a randomly chosen from Florida websites, a picture of a WKB approximation. And let's say this E50 is 0. And you can see that when potential is non-zero, the green thing there is negative, you have this perfectly oscillatory solution. When the potential is positive, the equation does not have any real solutions, but the imaginary solution makes sense, and you have something which is decaying exponentially. And there's a transition region. So this is the review of this classical method, but which is still used, and it's extremely accurate. So microlocal analysis from the semi-classical perspective is a generalization of all these ideas to more general operators and functions. So what you consider is phase space, position and momentum space. So I'll just talk about Rn cross Rn, but this could be manifolds, and this would be a cotangent bundle of a manifold. I'll have some parameter h, which is small, and that is the effective wavelength of my problem. Classical observables, like psi squared plus v of x, are functions on Rn cross Rn. And then we have a quantization procedure for functions. Well, maybe one needs to impose various conditions. I won't get into this. you basically replace psi by h dx. So if it is a polynomial in psi, you get differential operators. And there are different ways of doing it. It is convenient to use a way in which, from real classical observables, you get self-adjoint operators, and there is a way to do this. So this is we obtain now the semi-classicals use differential operators. So sort of easy examples that we already saw. If I have a function, just my function, classical observable is just xj, a coordinate function, the operator is just multiplication by xj. If it is momentum, psi j, coordinate of the momentum, then its quantization is just this derivative. And on the level of this type of theory, on the level of this type of theory, the classical quantum correspondence manifests itself as follows. If you take a commutator of two quantizations of two classical observables, you get to leading order 0. So if h goes to 0, this goes to 0. So on the to leading order, operators commute. However, if you look at it a little more closely, what you see is that the quantization, the commutator of quantizations is a quantization of a classical object, the Poisson bracket, which will be central in this talk, as it was, for instance, for different reasons, central in yesterday's plenary talk. The Poisson bracket in this case is just the Hamilton vector field of A applied to B. And remember, Hamilton vector field, the flow of it is classical motion for the observable A, and hence, we have connection between the quantum mechanical picture and the classical picture. And there's always an error. And there are many different ways to quantize classical observables, but everybody will agree that in your quantization procedure, you should have this property. And the example is the Val relation. If you take the quantization of psi k and xj, you just get h over I times delta function. So since I had to tell some jokes, so I had a paper submitted to a more scientific journal, not a PD journal, years ago. And we all get papers rejected, it's a normal thing in life. And the paper was rejected with the following report. If by microlocal analysis he means WKB, then it's extremely well known. And I reported to a senior colleague who said to me, it sounds like a conditional rejection, because what if not? So, whoops. Oh gosh, this is like vengeance of the editors of that unnamed journal. Okay. So, in mathematics, we want to solve equations. And, the simplest equation is you have a quantization of some observable, P, and you want to solve P equals F. You want to solve for U given F. And, of course, you want to do it in some quantitative way. You want to estimate U in terms of F. So one advantage of this point of view is that you can try to, rather than estimate U everywhere, you may try to estimate U locally, but in position and momentum. I could have A to be essentially a smooth, characteristic function of a set in X and Xi, and I can say, can I estimate the part of U where positions and frequencies live in that set by F? And the answer is, and this is something that will be important in my talk, is that you can do it as long as the support of A is away from the set when P is equal to 0, which sort of is kind of obvious. When P is different from 0, you can estimate, if P was a function, for instance, perfectly decent example of X, if P does not vanish somewhere, then of course you can estimate U in terms of F there. It gets more interesting if you look on the set P equals to 0. In that case, you cannot estimate U or part of U living on the support of A by F alone, but you can do it if you can geometrically control it using the Hamilton flow. And even though this will not be so important in my talk, what is important is the role of the Poisson bracket. So this, in a nutshell, is sort of the semi-classical quantization and its uses. So I will now talk about an example coming from modern physics, which sort of, to me, became a sort of a laboratory for applications of semi-classical analysis. So TBG stands for twisted bilayer graphene. So everybody probably knows graphene, because graphene is obtained from graphite. Graphite is what's in pencils. It's the carbon crystal, and graphene is a single sheet of carbon atoms. This was studied by theoreticians since the 40s, but it was only produced in this century, 21st century. And it was produced, honestly, by using Scotch tape, attaching it to graphite, and obtaining single sheets of graphene. I had trouble believing it for a while, but it's true. And, this was done by Gaiman-Novoselic. Oops, sorry, this is more expensive. This is Gaiman-Novoselic, which shows that great science can be done on no money. We probably should get used to it now in this country, So then, of course, people, when there was still money, started doing more complicated things. And one complicated thing, which I can't really get into details of, was twisting two sheets of graphene and also twisting other materials. One advantage is that, when you twist two hexagonal lattices, you get what they call a moiré pattern. And moiré pattern shows a sort of a hexagonal lattice, but on a larger scale, approximately. And that has many advantages in itself and for other experiments. But what was experimentally verified, 7 years ago, first by an MIT group and then other groups, is that you get some magical properties at a magic angle, which is different for different materials. For this particular thing, it is about 1 degree. And this was remarkably predicted experimentally. I think they predicted 0.98. This is a remarkable prediction by theoreticians, Bistritz and MacDonald. And in fact, they and the leader of the MIT group got the Wolf Prize for it a few years ago. So Yuan Cao, who was the sort of lead experimentalist behind this discovery, is now in Berkeley. So we went on several visits to his lab. And this is my former postdoc, Mengshuan Yang, who made interesting mathematical contributions to this subject. And here is Yuan with the Scotch tape. You see that the most important tool of a modern condensed matter physicist. And I went there too, but I forgot to take a picture with the Scotch tape. And since I'm not an experimentalist, not a physicist, what am I saying? I'm not a physicist. The only conclusion from this visit I could make that Yuan is experimenting with his hairdo, if you can see this. Yes. But actually, our motivation came from the following paper, which is a letter, as the physicists would call, from the Harvard group of Vishwanath, which was published 6 years ago, and it's actually quite popular. This is not like super popular, but it's respectable in physics. This is from Google Scholar. And they simplified the Bistritz and MacDonald model to make it better mathematically. So I'm afraid I have to write some formulae. This model is built, so this is actually even simplified compared to their model, but let's just stick to that. Their model is built out of a non-self-adjoint or non-normal operator like that. This operator is essentially the Cauchy-Riemann operator. So Cauchy-Riemann operator is the operator which characterizes holomorphic functions. D bar is 0 if of u is 0 if and only if u is holomorphic. So it's built of the holomorphic function and has some potential and has a coupling constant alpha. And what was nice for mathematicians in this paper was alpha was a dimensionless constant, which is, great because there's like the physicists always think in terms of real quantities, dimensions, but we actually love dimensionless constants, at least I do. So out of this operator, you build actually a self-adjoint operator which governs the system. And this V has to have various properties. It's symmetric, it's periodic with respect to essentially triangular lattice, has certain properties under twisting and certain sort of reality properties. So but what I would like to emphasize here, that we have an operator which is non-normal. It's built out of d bar plus alpha coupling constant times a vector potential, matrix valued potential, and there are some symmetries. And so here are some examples that you can build this out of the actual original Bistritzer-MacDonald potential. And as I said, this is not quite the model from that paper. This is a model that was introduced in a note with Jeff Galkowski, but it has many similar features and it's easier to describe. And observe that this is a semi-classical problem, because if I call H to be 1 over alpha, if I divide it by alpha, I get H in front of dz bar. So I'm quantizing a classical observable. In fact, that's how it started. A colleague in physics, Mike Zaletal, told me about this paper 5.5 years ago, and said there's a semi-classical problem and there is a question which we don't know how to answer. And I have to say that 5.5 years later, they don't know how to answer it, but neither can I, but I'll tell you about it. And I should also say, just in all honesty, that 6 years ago, people thought that there would be more magic angles. So alpha, by the way, I should say alpha is 1 over alpha is the angle of twisting. So in this problem, H has nothing to do with the Planck constant. H is a small angle of twisting. And but now this hope really has not materialized, and it's kind of a mathematical curiosity to study the limit as alpha goes to infinity, but I like it. And some people still like it in physics. But what really got my attention and fascinated me about this operator are its unusual spectral properties. This is, for experts, an elliptic operator, let's consider on a torus, because it's periodic potential, so it's on a torus. So, an elliptic operator, which is Fredholm of index 0, typically has discrete spectrum. Certainly true if the operator is normal. But this operator has unusual spectral properties, and it's like that. This is the spectrum as alpha changes. It's a fixed lattice. The spectrum does not change, except at certain values of alphas. It's the whole complex plane. So I had been in this business for many years, but I've never seen a thing like this before. And but actually, there was an example before. I was told by Bob Seeley, but he constructed an interesting family of operators on the circle, which had a similar property, namely that the spectrum is empty in this case, or the whole complex plane for discrete set of values. So this is an exercise in calculus to see that this is true. But he did it partly to show that non-self-adjoint operators are weird, and they may be elliptic, Fredholm index 0, yet they may have crazy properties. We should stay away from them. But in this paper, this operator played a central role. And how is that? So, well, in physics, in condensed matter physics, you have this self-adjoint operator built out of these d alphas, and you consider it on the whole plane. It's periodic. To study its spectrum and properties of materials, it is useful to study a family of operators with periodic boundary conditions with this parameter k. In this case, it's just studying this family of operators. K is a complex number. Now, this operator is self-adjoint and elliptic, so it has discrete spectrum. And of course, a moment's reflection shows that the spectrum comes in positive and negative pairs. So the spectrum comes in these pairs. And what's of interest is something called a flat band, namely at 0, namely the case in which E1 and obviously the negative eigenvalue are identically 0 as k varies. And a moment of reflection shows that this is equivalent to what I showed you before. This statement is equivalent to d alpha having all of the complex plane as its spectrum. Because, if 0 is an eigenvalue of this operator for all k, then d of alpha plus k has to have kernel for all k. And it's actually an equivalent statement. You know, this is a great paper, but I wish they had said it or knew it, because it would have made our life easier to understand, you know, break the language barrier. And so this is what I just said. The spectrum on the torus of d alpha is the whole complex plane, if and only if we have this flat band. So I cannot explain it here, but flat bands which have, you know, topologically non-trivial, I mean, I can say more about this, but imply interesting physical properties, such as potentially superconductivity, though I admit I do not understand that part. But mathematically, the question is studying the set of alphas for which you have these flat bands, and also study properties of the solutions to this operator. And one of the interesting things in this paper, this physics paper, and that was in fact the question that I was asked, was that numerically, Tarnopolsky and company observed that there's a quantization rule for alphas when you take this Bistritzer-MacDonald potential. And namely, they are spaced, equally spaced. It's a little different than what's in their paper, but it's an adaptation to this simpler model of the result. So in a paper with Becker, Embry, and Wheatstone, we gave a different characterization of these magic alphas, and then could actually have more accurate computations. So this is not, the quantization is not 3, but it's some number, which you know, turns out to be 3.03. And we still don't know why this is so. The key fact behind the analysis of this is that even though the spectrum you know, is the whole complex plane only for a discrete set of 0 is always in the spectrum. There's always a state, so-called protected state, because its existence implied by symmetries of the problem. There is always something in the kernel that's non-trivial. And the following fact was actually, in a sort of simpler case, already in the paper by Tarnopolsky, but this is a generalization of that, is that you get an alpha which is magical, where you have the whole plane as the spectrum or a flat band, if and only if u has a 0. Now observe, u is a vector. These are two functions, two complex valued functions. So complex valued functions in 2 dimensions will typically have a discrete set of zeros. You have another complex valued function has a discrete set of zeros. So it's a rare event when somehow those zeros will coincide and both components will have a 0. And in fact, the number of those zeros is the multiplicity of the flat band, and the flat bands can appear with multiplicities. So we would like to understand the structure of this protected state as alpha goes to infinity, as h goes to 0, because if we understood it, well, we could maybe understand the number of zeros and then get this quantization. So as I say, we have this protected state, non-trivial, of course. And this is the nice feature of this simplified model, that it's essentially scalar. Because, you know, if you look at the system I had, you could reduce it to a scalar equation. That was really the point. And the scalar equation, you pay a price. There is now a second-order equation. And it looks like the Schrödinger equation, except that instead of the Laplacian, you have d bar squared. And again, this was kind of a new type of equation to study for me. And we still don't understand various basic things about this class of equations. And, you know, a 0, you can see, of u corresponds to a 0 of u and simultaneous 0 of u and d bar of u. And this u0 actually has sort of a 2-dimensional WKB structure to some extent. So this is a picture of 1 over alpha log. So I would like to point one thing which is striking. There's this hexagon, and blue is -1, the deep blue is -1. But of course, since alpha here, alpha is 20, the actual log of u naught would be minus 20. So this means that the solution is exponentially small near this hexagon. But it has a nice oscillatory structure, both in this deep, exponentially small abyss, but also in other places. And this is visible in movies. And in this case, the zeros have to be created for symmetry reasons at the vertices of the hexagon. Every time a zero is created, we have a magic alpha. And this is, how it looks like when alpha changes. So this is beautiful structure, which I admit I don't understand. So, but we have some results. So let me tell you about this result. So the first result, which is based on essentially WKB methods, though not the standard ones, is that the bands get squeezed exponentially. So this is in a way why in this very nice model it is hard to find a perfectly flat band as alpha is large, because many of them, roughly alpha of them, decay exponentially. So in other words, the way to put it in words, every small angle wants to be magical because it's very small. And this is based on the geometry of the Poisson bracket for the corresponding classical observable for my operator, which was given by this formula here. So this is for the Bicester-McDonald potential, and then other potentials. And it's a consequence of famous work in PDE, starting with Hermander. That was the WKB construction behind his paper, in which he gave the necessary condition for solvability of linear PDEs. And the analytic case was done by Kawai Kashiwara, and direct semi-classical argument was given in the paper with Denker and Shestrand. And, indeed, so these are the bands for my problem. Bands means eigenvalues of the operator from, d star plus k bar, d plus k on off diagonals. And you see, so this is the first magic angle. Now, boom, we got a flat band. And the next one will appear at 2, but you sort of see how more and more of them are coming down as you increase alpha. So I mean, it's not maybe too exciting to watch the rest of it, but you believe me that they start piling down there. So mathematicians like to count things. So the question, can we count the number of these exponentially small eigenvalues? And that actually seems to be very difficult. And the indication for it is the following, actually beautiful recent work by Hittrich, Shestrand, and Fogel, who studied for different reasons the characteristic values of the d-bar operator on exponentially weighted spaces on Riemann surfaces, but in particular on the torus. And this operator now is a perfectly, scalar, just dz bar. And then my potential is just dz bar of phi, where phi is a real valued function. So, compared to our problem, we have a complex valued function, which is matrix, complex valued and matrix valued. And it's a complicated thing, but they get actually beautiful formula for, and kind of at first unusual formula for the number of exponentially small eigenvalues, which is given by integrating the leading part is the integral of the Laplacian of the phi over the set where Laplacian is non-negative. And this is for small tau. For larger tau, to get the formula, they have to solve a free boundary problem, which is kind of interesting. Well, an easier problem is, can we count the number of EJs less than E and let E go to infinity? Fix alpha. And that was actually computed, I'll say, by actually a Berkeley undergraduate, Henry Zheng, who got this formula. So this is a counting of eigenvalues, and this is the error. So this formula, if the error was replaced by little o, this is the famous Wahl law from 1912. But here we are dealing with a system, 4x4 system, because we built this, so if I draw an operator, two blocks. So actually, the lower order terms in spectral asymptotics for systems were only described in 2013. This was 1912, 2013 by these authors. And what Henry did, he calculated the formula, and somewhat to our disappointment, showed that those lower order terms vanish for our operator, and hence all you get is that the lower term improves. And of course, there has been, a whole history of the subject of studying the remainders in Wahl laws, etc., etc. So another result is a result about this classically forbidden region, seemingly classically forbidden region, where our solution is exponentially small. And the result with Michael Hitchik and with Zhongkai Tao is that, indeed, if you have a solution to this problem, then it is exponentially small in an alpha-independent neighborhood of the hexagon. And this result, even though it has some technical differences, but it's inspired by work on analytic hyperlepticity, and again, the geometry of the Poisson bracket. So these are works of Yegorov, Kashiwara, Shestran, Treprohimonas, and other experts in those days. And in particular, the key thing, which is sort of stays in our proofs, is a crucial idea of Kashiwara. And then actually Shestran gave a different proof of the part of the theorem with Hitchik. So actually there's a general result, which is a local result about solutions to semi-classical PDEs with systems also with analytic coefficients, that if you just have a local solution and you have some normalization, and you know that whenever Q is 0 above this point x naught, the bracket of Q and Q bar vanishes, but the next bracket does not vanish, then the solution is exponentially small in the neighborhood. My training was in C-infinity category, so this is not true in the C-infinity category, and I still find it kind of amazing that from information at the point, you actually get information in a neighborhood which is H-independent. But at the corners, so this actually applies away from the corners on the hexagon. At the corners, as you can see, it's much more degenerate. You need so many brackets. So we couldn't use any type of general result or general philosophy. So we used the same idea of Kashiwara, but the specific structure of the operator near the corner was essential here. So since, every talk is supposed to, somebody told me I should have a proof. So I'm not going to prove this, but I give a proof by example. And this is the simplest example. The simplest example is given by Q, which is psi plus ix squared. And the quantization of it is just this ODE, okay? And of course, this ODE, before I say about the ODE, we compute the Poisson bracket. So remember, this will be partial derivative of Q respect to psi dx applied to Q bar minus partial derivative of Q respect to x times partial derivative with respect to psi of Q bar. Quick calculation shows that it's 4ix. And the second bracket does not vanish. And at 0, if I take x equals to 0, the only place where Q is 0 is psi equals to 0. The bracket, of course, vanishes. And we solve the equation. The equation is solved by ODE method. And this is the solution. As you can see, this term here is going to be exponentially large for x positive and exponentially small for x negative. But if you want it to be normalized in L2 in some neighborhood of 0, well, U0H has to be exponentially small, because otherwise the growth will kill us. And that, of course, means that the solution itself is exponentially small. So, of course, this is not quite the model for our case, and also you can't put things in normal form, but at least this gives somehow an intuitive reason why such a thing may be true. it's interesting to see how the geometry of the Poisson bracket of Q and Q bar affects the solution. So we know when it vanishes, but with some non-degeneracy, the solution is exponentially small. So you can change the potential and keep all the symmetries and see how the geometry of the Poisson bracket affects the solution. And you see that there is a sort of classical quantum correspondence here. It's particularly striking, as we will see in a moment, when the Poisson bracket is zero on a large set, because then your solution will be exponentially small on a large set. Yes, it's coming up. You see here, we have bracket which is zero on a large set, and the solution is exponentially small on a large set, as predicted by the theorem. But still, to me, this is kind of a postmodern revisitation of those old ideas. So now about the problem of quantization of magic alphas. Well, so for this potential, the numerics show that the quantization is given about 3.03. And actually, the set of alphas that's a set which is complex. So alphas are complex numbers. The physically interesting ones are real. I have been trying to convince my physics friends of the importance of the complex ones, but unfortunately without much success. But I'll tell you why the complex ones matter. Complex ones matter because if you change the potential, they start moving. And the real ones may escape to the complex, or complex ones might come together and become real. And this set has this beautiful structure which I do not understand. We do not understand. We understand various things. So for instance, if you take a sum of alphas, so these alphas here to the power -1, -4, you get 8 times pi divided by square root of 3. And if you take any power, so that's from papers by Becker, Humbert, if you take any power, then it's always a rational multiple of pi over square root of 3. And this shows, this was my young collaborator was kind of, pointed this out, that this shows that there are always infinitely many of alphas, because if you had finitely many, then you could use Newton's identities, and you would see that pi over square root of 3 is a solution of a polynomial with rational coefficients, which it can't be. So that's a kind of recreational mathematics. But you see, this is how the set changes when you change the potential. And basically what we see is that if the geometry of the Poisson bracket is regular, we have a regular distribution. And when it is getting crazy, crazy things happen. But we don't understand it. So now, one reason why this Bistrica-McDonald potential is because the set where Q vanishes is complicated. As I mentioned in my sort of review of microlocal analysis, the action happens where Q is 0. That's where somehow my solution is localized in phase space. And the structure, so here is my sort of attempt to describe this surface. So this is Q is a complex valued function. So we are in phase space is 4-dimensional. So it's a surface in 4 dimensions. And, it has 2 ramification points. It projects to the torus. It's smooth except at one point. But somehow it is complicated to build an approximate solution which lives on this surface. We just don't know how to do it. And an additional complication is that it's exponentially small in so many places. So this stops us. And so far, normally I get my figures drawn by my junior collaborators. So, actually not so junior, like Simon Dyatlov is now a famous professor at MIT, but I asked him always to draw pictures for me, but he refused to do this one. So what we thought, and actually this was discovered by same Henry Zheng, the undergraduate who worked with us on this project, is to find a potential with a simpler characteristic surface which has all the symmetries and has all the alphas. And this is the potential. It's obtained from the potential U, which is obtained from the Bistritzer-MacDonald potential using this non-physical operations. This has all the symmetries, and it has a set of magic alphas, and has the property that now on the characteristic surface the bracket is identically zero. So the operator, if you remember, the bracket corresponds to the commutator. So the complex conjugate corresponds to taking the adjoint of your operator. So this would mean that the operator is normal if it really commuted with the adjoint, which would be great. It's not quite normal, but it's kind of normal on the characteristic set where the action happens. And this is now a much simpler characteristic surface. It's two tori, which are Lagrangian, so symplectic form vanishes on this tori. It has to happen that this tori touch a point, 3 points, with high degeneracies of this touching. That's what complicates the problem. And the set of magic alphas, from a distance, it looks exactly the same as the Bistritzer-MacDonald. It's really weird, and I don't know. This is the set. And yes, and the characteristic surface is given by this two tori. So there are graphs of an explicit, for this potential, an explicit real valued function. So this is in collaboration with Semyon Dyatlov and Henry Zeng. And if you rescale the original potential case, rescale it so that the spacing on the real line is the same, then you can see that those sets are not quite the same, but they have very similar structure. So what we did, and this is not yet rigorous, and maybe never will be because it seems very complicated, we constructed a WKB state which has the correct symmetries, and we know that then it has to agree with the protected state. And to show it, this is in eyeball metric, it's extremely good. You see that the bottom one is the actual protected state, and the top one is a WKB state. And WKB state is constructed by using the fact that at some places we actually can use sort of a WKB construction, and the fact that locally multiplication by any locally holomorphic function is still a solution. So you can sort of modify it. And at the center, we build something out of special functions that are an approximation. The equation is an approximation to our equation. This is actually the part which would be tricky to really make proper mathematics out of, though we will see. And then you match the two things. So this is what I say, that we don't have a rigorous justification of this. And here is a picture of how it changes when alpha changes. So it becomes more oscillatory, but it's a good approximation. So how does this relate to the quantization of magic alphas for this potential? Well, we again look at the solutions to our equation, and recall the zeros of this give me, if I have a zero of this function v of alpha, or the zero of u and of d bar of u, somewhere on the torus, I have a magic angle. And in this case, symmetries force and other considerations force that the zeros have to be at the corner, at the vertices of the hexagon. There are two vertices of the hexagon in each fundamental, on the torus, on the fundamental domain. And if you look at the hexagon, so this is our WKB solution. This is the edge of the hexagon, and the matching gets better as alpha increases. And what you see that actually on the edge of the hexagon, this solution just behaves like cosine of alpha phi being our phase function. So now, if there is a zero, finding a zero of an approximation, that's extremely unreliable. However, we know that if a zero occurs, then for larger alphas, two zeros appear on the edge. Those zeros don't have the property that d bar vanishes, but they are zeros of this function u naught on the edge. So I can count the number of zeros on the edge. If we can count the number of zeros on the edge, then the spacing between alphas is given by this formula. And in this WKB construction, on the edge, the solution behaves just like this, with incredible accuracy, at least, so it seems. And then, after all this, snowing you with Kashiwara, Hermander, and so on, everything boils down to pre-calculus. This phi was an explicit function. X of t is a parametrization of the edge from t goes from 1 to 2. So that L is just given by this formula. So then you do your trigonometry. And kind of amazing, actually, for these potentials, all sorts of wonderful things happen, like this pi square over 3. And here it's 1/4. So now this is actually a number, 1/4. So this was, we were counting the number of zeros here on this edge, which is sort of half of this picture. So how does this compare to the actual numerics for the problem? Well, it's pretty good. I think once alpha is large, it's 1/4, 2498. So at least in this case, we have a reasonable, physics acceptable argument for this quantization rule, which probably we'll see if we can make it into real mathematics. But it's an interesting, different WKB construction than the ones we started with. So I'm about to finish, but let me just flash in front of you some recent advances in application of microlocal analysis, of which there have been many. I had to make the print very small because every time I prepared the table, I forgot something, and it's still very incomplete. There are various interesting results here. For instance, maybe I mention one that's connected to various things. This is a recent work of Huang, Song, Zhongkai Tao, and Zhang, which shows that if you take a negatively curved surface with sort of funnels at infinity, then Strihat's estimates, which are sort of central in PDE, hold without any loss. And that relates to this work in the beginning and the fractal uncertainty principle of Bourgain and Dyatlov, and now also of Alex Cohen, because those are the methods combined with harmonic analysis methods that give the Strihat's estimates without any loss. So that's one kind of example of applications of this subject. So thank you very much.
Thank you. Are there questions? Yes.
Could you expand a bit on the difficulty of making the approximations rigorous?
Well, the difficulty, okay, so I'll tell you, the difficulty, let's just have this picture here. You see, the difficulty is the following at this stage, that we have to get this, we approximated our equation by Fourier series, what I'm saying, Taylor series at the origin. That's how we got Bessel's equation, okay? And then, we have this freedom of multiplying things by holomorphic functions. So we multiply by another Bessel function of the holomorphic variable, but it's all based on the approximation by Taylor series. It's remarkably good, but of course, it's not really accurate away from zero. It can't be. And you have to match it away from zero. So what it means is that basically one would have to develop a theory of equations which depend on this extra parameter z in a holomorphic way in a function of z bar for a Bessel-like equation, and then use that to match it. And that seems difficult. And it's kind of, we were just discussing the other day whether we were not sure whether we are doing 19th century mathematics, 20th century, or 21st century, because it's kind of a, you think of z and z bar in many of these things as independent parameters, but of course, ultimately, they are z and z bar. So that's the main difficulty at the moment to match it. We don't really have despite this good picture, we don't really, have a proper way of estimating this with errors which only depend on alpha and go to 0 with alpha. Here the errors will also depend on z, and that makes it difficult to match. That's at least that's our main difficulty at this moment.
Thank you. One other quick question? Okay, and then before we thank Professor Zworski, there will be some brief announcements afterwards, but let's thank Professor Zworski again.